We didn't start the fire. Welcome to The Big Puzzle. In this podcast, we explore the subtle connections between science, religion, politics, economics, and history. One piece at a time, we unveil the big picture of this shared experience that we call life. So I don't know if the microphone captures this, but there's some helicopters flying around, and this is the reason why they are there. So last night we had a beautiful fire in the mountains, and that prompted me to do this video. I've been collecting ideas about how to present this topic, but then this was kind of a sign from heaven that I should do it now, so I don't want to delay it anymore. I need to start from, as usual, from several places and trying to connect things later, but I can start by talking about one of the problems that we have in society today, and there's apparently no solution for that. And that is the problem of specialization. So you might say, well, specialization, why would a specialization be a problem? Actually, it's one of the great benefits that we have in the modern world is that, we are not all farmers. We are not all trying to do the same things, and we specialize, and that optimizes the economic system. That is good. But I'm talking about another kind of specialization, that is the specialization in science. And we could say also in technology. Why is that a problem? Well, because now it's very difficult for people to collaborate, to come up with new ideas. In the past, there were some people who could, through study, learn everything that was to known in their time. Now we call them the Renaissance man. So somebody who knew about chemistry or alchemy, physics, or whatever they call it, medicine. So all the disciplines, they knew what humanity knew about that. That's kind of a stretch because different parts of the world had different levels of knowledge, but still there was this idea that you could know pretty much everything. After the Renaissance, well, that was very, very difficult to do because now all these disciplines went deeper and deeper in their knowledge, and it's impossible. You don't have the time to be on top of all the new developments in science. We call the people now who manage more than one field of knowledge, we call them polymath. And I think that until fairly recently, we had a few of those that are sadly passing away. So obviously Isaac Asimov is the one I would consider the last true polymath. Then, I also believe that Bertrand Russell was kind of a polymath in a sense. But after that, well, now, like I was saying, it's very, very difficult to know more than one discipline. And also there's no interest in science, apparently, for having generalists. So, in medicine, you have a specialist for this, a specialist for that, but usually you have a generalist that is somebody who basically would point you in the direction of which specialist you should go. You should go for your problem. So, but in other fields of science, you don't have that. Nobody's interested unless you're going to be, a high school professor of science. Higher level education doesn't have generalists anymore, and that is a problem. So, why all this introduction? Well, because when I was planning to do my PhD, I had to decide which discipline. So my high school was a high school that was oriented for sending people to become lawyers or become politicians. There are many famous people, some doctors that came from my school, the Colegio Nacional La Plata. And so I had all that, eclectic formation, learning about, psychology, logic, history, literature, whatever. But then I wanted to be an engineer. And I took me a while to decide which kind of engineer I wanted to be, but I settled for civil engineering, in particular construction engineer. I was fascinated by, these big projects like dams or bridges or roads, large buildings. That really, really fascinated me. How could we understand the stresses in the structures and the planning of the work and everything. So I became a construction engineer. Many years later, when I was considering to do my PhD, I had to rethink what I wanted to do. And the first part of my career was in geographic information systems, and in the mid 90s, when I was doing that, was a new technology and had to do with computers, which I didn't know how to program because of my father. So it was very, very interesting. Kind of, it was a confluence of many different things I liked. But later on, I did less and less in geographic information system, but I did really like that idea. So when I had the option to decide what to do, well, I thought hydrology would be an interesting thing. One other reason for choosing hydrology was that it was a field that was not really very explored, even though water is so important for us in so many different ways. But still, it was it's still a very fresh, not fresh water, but a fresh field. So you could be doing things, you could be inventing things, you could be figuring out things, and so I thought that would be interesting. But I also wanted to be somehow solving this problem that I was talking about, the over specialization. And I didn't understand how research funding worked, so I was kind of naive, but I had my idea of how I could help solve that. And now I have to do, another segue that eventually will connect. One of the things I always found fascinating was systems that with very little set of rules can create complex behavior. And we talked about that in a previous video. But in particular, I was always fascinated by Conway's Game of Life. So how very simple rules, and if you don't know about it, we can talk about it some other time. I don't want to go into another branch, but if you know what it is, well, you can see how these kind of mathematical beings come to life and reproduce and travel and collapse and die. It's very, very interesting. So in my mind, I kind of connected that with my GIS experience, and I thought, well, what if we find a way in which specialists can collaborate without collaborating personally? So the way I thought about it is say, okay, I'm a hydrologist. Let's say I'm a hydrologist. I was not a hydrologist yet, but let's say I'm one. So I'm an expert about how water flows. I know about infiltration, evaporation, runoff, and I know about, terrain and everything. So if I have a good terrain data set and soil information and weather information, I could create a fairly accurate model about how the water will move in nature. But I'm not a meteorologist, and I don't know if I could build a model for that. And also I'm not expert in erosion, so how would I do the interaction between the water and the soil and so on, right? But I say, well, but if I could, let's think about layers. So you could create the different layers, and I will be developing the layer for water. And for my layer of water, I could use data from other layers. So there would be one layer that had I don't know, wind, right? And another will have humidity, and another will have soils, another will have. So all these other layers are available for me in a way that I can, use data from them to build my own, to make my own model run. And then other people could use my model for theirs. For instance, somebody's researching erosion, and they could use the data from my layer, to build theirs. So in that way, you kind of create a fake universe or a fake planet in which every specialist is actually working in its own domain. But all those domains, through these layers, they're interacting. So I did some proof of concept. I built one using Excel. And if I find that, I would probably put some animations here about the things I did back in the day. And then I really started exploring that. So what would be those layers? How can I model those layers? I came up with what I call the disco ball raster. That is a way to represent rasters or grid information in a sphere and at different scales and how things would work. And I tested that. And I did all that on my own because I was very excited about the idea. Eventually, I created a blog in which I put some of the results. I even developed a language. I called it, how did I call it? Pseudo-natural language or modeling language or something like that, in which you could write saying, okay, grab the data from this layer, apply this gradient, and we're going to be talking about that from this other layer, and then so on. So I used it to show how I could use that to find meteors. But the one that reminded me of what happened last night was that I built a fire model. So, and then on top of that, I created an animal model. So basically, how would animals behave in the presence of fire? I had a layer for smoke, for wind, for I think I will be posting some things. If not, I will put a link to where I put all of that. Well, what was the problem? The problem, again, was that, research doesn't work that way. Nobody's willing to fund that. So once I got to the university, I tried to share my idea. I said, yeah, that's really neat, but, we have a NSF grant for doing this. So you have to do something related to this. I was not really excited, but, I ended up figuring out a topic that for me was interesting enough. And I already talked about that, is using pre-computed models. And I think that would be interesting for another piece of the puzzle that I haven't connected yet. So it was fun, and I really appreciate the help from Dr. Jones, my advisor, Dr. Nelson, the patience that they had with me. But I could never, build that model. So the other interesting thing was that, okay, I'm one hydrologist. Why should I own a certain layer? Well, the whole idea was that anybody could build any layer. And people would choose which one they want to use. So that will create kind of a Darwinism of models. So now the models are preferred by other specialists kind of survive, and the other ones die down. I call that, to try to explain to people, a Wikipedia of models. Right? So you just took care of your page, but you're contributing to everybody else's. So that was kind of a fun thing to do. But so what are we going to be connecting to all of this that I just said? Well, last time we were talking about fields, and how fields are basically numbers in space. And now I realize that what I was proposing was basically that idea, the idea of fields. Each of these layers would constitute a field, right? It was numbers in space. So I was talking last time about temperature, I was talking about wind, electromagnetism, gravity, some examples, and now you can see that all of those could be layers interacting with each other. In a previous video, we talked about attractors and repulsors, and well, attractors and repulsors are actually producing fields. So it's how do you know what is attracting you? It's because there's a gradient. Remember, we introduced that idea of what is the slope in your field. And we talk about complexity arising from simple rules, like I was talking about Conway, but also remember when we talk about the ants and things like that, it's really, again, it's about fields, right? So this interaction between fields produced through processes that we also talked in the past about system dynamics and Dr. Forrester and so on. This interaction between different fields, they produce nonlinearity, so things that happen, that change suddenly or accelerate fast, or that they become stable on the other hand. So you have, again, the idea of equilibrium. So you have stable equilibrium, unstable equilibrium. You have thresholds. So those thresholds are defined by interactions of all these fields, right? So as you can see, this kind of connects everything together, right? But last time when I was talking about fields, I mentioned that, well, all these fields that I was talking about, they affect inanimate objects or just matter, right? That they don't have a will. So how do we deal with the idea of will and fields and attractors and repulsors? Well, the way we can make them work together is if we think that we are generating fields. We are generating many, many fields around us, and might not be physical, or at least they might be physical, but we don't understand them yet. But you could be repulsing people, so people don't want to come close to you, or you could be attracting people. People enjoy being with you, so they look for opportunities. You create a gradient, towards outward or inward to you, right? Based on how you affect those fields. That would make societies happen naturally because of the fields of several people, that they join together, and now you have common goals, and you have also a sort of common consciousness and things like that. But also we could think about moral fields. So we are all exposed, and we talk in the past also about opposites. We talk about repulsor and attractors. We talk about how important it was to have opposites. We talk about entropy, that the entropy reduces the differences between the opposites until you can't extract anything from that. But we are all exposed to those opposites in our lives. And we could talk about moral fields, right? So things that attract us, but we decide not to follow because there are other more important fields for us, that we overimpose over those, let's say, more animal fields. And that's the way we behave, and by doing that we affect other people that might follow us or might get away from us. So I wanted to kind of bring that idea of fields affecting absolutely everything, and not only in the physical realm. And well, I think I will save the next for another video, but just as a teaser, in computer science, you also have a lot of fields. But for me, it was very interesting. I was learning about how AI creates images, and one of the ways is through a very clever process that is called diffusion. And I will probably, oversimplify it. I don't fully understand it myself, but I will try to explain what I think it happens. So the way the diffusion works is by reducing noise. So think about this image that you're seeing now, my face, the seed and whatever. So you can add noise to this image, and that means that you will randomly change the intensity of the RGB color for each pixel, and you can do it more and more over and over and over, and eventually you will just see kind of a white noise, like the old TV sets, that is just random colors all around you. There's nothing from my image. Well, the way diffusion works is by reversing that. So basically you start with a random noise image, and then you tell each pixel to which color should it go. How does that work? Well, that's incredible. But the way it works is that you randomize, you create noise to this image millions of times. So basically, if you think about colors like a position in a space, you have millions of paths starting, from this, color, whatever it is, this skin color, that will go in different paths, but it usually ends up going, in the similar direction. So what they do is they look at all those paths that each pixel takes in this color dimension, and they create a field. And the field is basically saying, okay, pixel, if you're in this color, you probably follow one of the paths that reach there. So let's create a field pointing you in the opposite direction. So they're trying to send that, back to where it started. Since you don't know, the code doesn't know which pixel will go where, right? They just work with those fields. Basically start with random and start forcing it, thinking like, pushing it, or having wind or gravity or whatever, pushing the pixels to the color that they should have. It's amazing, but for me it was very, very interesting to see, these fields. And the interesting thing is that as time progresses, the fields go change until they get really close to the image they're going to produce, and the fields become very stubborn. They, okay, if you're here, you go here. So it's kind of the whole field is changing through time. So I don't know if that made any sense, but for me it was very interesting to see this concept of fields also applied, in other fields. And obviously you see them in math, you see them obviously in physics, in many, many places. But I want to connect this eventually to the simulation. Why I believe we are in a simulation. And that still lacks a piece that I will hopefully cover soon. So, well, I hope that you learned something new. I hope that I made you a little more Renaissance man or woman. And yeah, well, hope to see you in the next one. Bye.